Today, Aziz is going to tell us about simplicial distributions on suspension scenarios. Okay, yeah,
Thank
please.
you, Cihan. Just 1 minute. Yeah. Okay. Okay, so I want actually to start from this phenomena from quantum theory, the measurement scenario, to just to show the mathematical phenomena from this. Okay, the mathematical description from this. So we start from pipe. This is not good. This one. With bipartite, measurement scenarios. People remember this as Alice and Bob. Yeah. So when Alice and Bob have as this measurement that shared the same experiment system. So this one like have A1, A2, LA, and let's say one, this B1, B2, BN1. And they can share together like this. This Alice decide to take this one, this measurement, and this one, this measurement. So they doing the experiment together. We can only do the experiment together, and there is a result. Let's say the result only plus minus or 0, 1. This the outcomes. In this kind of experiments, like they can repeat this experiment. No one can do this alone, but they can do this together when everyone chooses his measurement. Okay, this one chooses his measurement, this one chooses his measurement. They can repeat it many times, million times. They can repeat it many times, and see what is let's say like this one choosing this and this one this A1 B2. So the results could be, this is the result, could be 0 0 like both 0 or 0 1 or 1 0 or 1 1. So they can do it many times as they know what is the probability, right? When just stabilize like it's doing this million and see, okay, there is some probability here, like the probability to get 0 0, like this is the result 0 and this is the result 0. For example, it's a quarter, and the result to this to get it's something like half, and for this is 1 over 8, and this 1 over 8. Sum is 1, of course, yeah, like this. And but there is many probability there. Like of course there is another, like for example, he can choose A1 still, but this one B4, for example, the measurement he chooses the measurement B4, and there will be some probability. So what can't happen here in the result, like it can happen that this will happen, like maybe someone for you can tell me why. It can't happen that, for example, this is let's say half, 0, let's say quarter. This can't happen. Why? Because they have share measurement here, which is A. Because from this we can know what is the probability for A to get 0. Now from this table, the probability for A to get 0, this is A1, to be 0, or to be 1. To be 0, I should sum this, right? 3/4. And to be 1, of course, it's quarter. But here it's not the same, you see? It's not the same. So it couldn't be something like this. So there is some rules in this, okay? There is some equation that should satisfy, which is called the non-signaling equation. Okay, so for example, this could be like something like this: 1 over 8, 5 over 8, 3 over 8. No, it could be 2 over 8, 0, for example, right? Yeah. So this is okay now because both give me the same. Okay, like to be 3/4, not 3/4, 6 over 8, 3/4. This is what I learned in school. Yeah, I don't know. It's correct. Okay. So it's okay like this, but you imagine like there is money in non-singular because there is money measure. Yeah, you see there is money some shared. So this is the rule. So the other thing one can think about, okay, maybe this all coming from something like this, like maybe we have a table for all the measurement together, like table like this. It's hard to write all the table, but something table like this, which okay, here like 0, all of them 0, and here maybe all yeah, well, there is many like this, right? And maybe this table induce all of the tables, right? Because like we see like the big table induces a smaller table, right? So maybe there is table like this that induces all these tables of probabilities, but it's not the case. Okay, so in experiment we have this what called non-signaling, but we don't have always this. So this in quantum theory, not always, yeah. In classical physics, it's always like this, but in quantum physics, no. There is proofs of some cases that it's not happening, like that there is some global table, okay? And this is what calls the phenomenon of contextuality. So in this case, the tables, these tables, called contextual or non-classic, okay? So this is if, maybe let me write it, if the tables of probabilities are not coming from global table, let's say this is like this, here, then the table okay, the table of probabilities, okay, I say maybe I mean the tables of probabilities, okay, anyway, the table are called contextual, okay, or non-classical, non-classic, okay. Okay, so this is the phenomena. So in quantum foundation, people are interested in like understanding the geometry of this. One of the things that are interested in is this understanding the geometry of such a table. Like we have, for example, I will give you some maybe small example. Of course, here I choose 2 outcomes, but it could be more outcome, okay? But let us choose maybe the most easy, like one which we have like A1, A2 here, and B1, B2. So in this case, we have 4 tables, right? This is called, and of course, we have 2 outcomes. This is called the CHSH scenario. This is a famous scenario that people understood it very good, like everything known about this, almost everything known about this scenario. So A1, B1, we have this table, and we have A1, B2, and so there is a probability, like there is P0, 0, P0, 1, P1, 0, P1, 1. You know what I mean? Like this is the probability there, and there is here also. Maybe I should write here that this is for A1, P1, or maybe I can choose another letter. Okay, and of course there is 4 tables. Okay, A2, B1, A2, B2. So how many numbers we have? 16 numbers. So we can think about this table as something inside a subset of R16. But of course, there is some equation. They satisfy some equation. What is the equation? For example, the sum of this is 1, right? Sum equal to 1, sum equal to 1. There is 4 like this, sum equal to 1. And there is the non-signaling, like the sum of this should be exactly the sum of this, right? Or the sum, or when B, like it's, I will find where is the B0 here and where is the B, yeah, the non-signaling plus non-signaling. So this give me a polytope inside R16, okay, inside this. Okay, there is even 0, 1 between the what? Yeah, with non-negativity even between 0, 1. Yeah, or non-negativity is it's enough, right? We should remember also there is another, yeah, in this. Yeah. because every probability here it's between 0 and 1, right? Yeah, so this is give me a polytope. And what we are interested in this polytope. So there is a polytope, something like this. Okay, of course it's in higher dimension, but I want just to, yeah. And inside this polytope, there is the ones that are classic, right? Non-contextual, that coming from global things. So inside this, there is another polytope. Let's say this. Again, this is in higher dimension. It's something hard, but it's just to understand what happens. So people interested on vertices of this, especially contextual vertices, like vertices as this, like not in the green. The green, it's a classic one, the non-contextual. But here, there is contextual vertex, yeah. And this one, yeah. So people are interested in finding or characterizing, yeah, or contextual vertices. And two, for example, this finding this this here there is equation that decides this hyperplane, right? That divided between the classic area and the non-classic area, right? So this is called the Bell inequalities. Okay, like here is there is Bell inequality. So finding the Bell inequalities of this polytope and other things. Okay, we will focus on these two things here. But first of all, let's actually write a mathematical language for this. A mathematical language that Cihan come with is a simplicial distribution theory. So let's explain this using simplicial distribution. Simplicial distribution, it's like some theory that describes this, or describe maybe more, but it's a good like mathematical way to describe this using simplicial sets. Using simplicial set. Okay, so simplicial. Now we are going to talk about simplicial distribution. So first of all, simplicial sets. Maybe you don't know, right? The simplicial set is continuous. Yeah. So let me explain what is simplicial. You know topological space, right? So and you know maybe simplicial complex. No, maybe you for okay. Anyway, there is like you can think about simplicial sets that like something like simplicial complex is something that you have vertices and you have it's like generalizing graph because in a graph you have only edges between, right? Maybe here another edge. Okay, like this is a graph. Okay, but you can have also triangles. So you have like this field is a triangle, and maybe this one also triangle. And maybe you have pyramid here. Yeah, this is also field. So you have more like between the vertices you have more things. Okay, so this is simplicial complex. Okay, but there is topological space. Okay, topological space defined by properties like something that there is you know open sets that. But you are it's good to build simplicial sets in the way that you know the dimension of this. Like there is vertices, which is 0 simplices, because 0 simplices. And 1 simplices, which is edges, and 2 simplices, which is triangles, 3 simplices, yeah, which is okay, and things like this. So we can put them in a way that how they glue together. We can only describe how they glue together. So we choose sets like set x0. This is the set of vertices of the topological space we want to build using vertices and yeah. and there is x1, which is the set of one simplices, like edges, and there is x2 triangles, x3, so on. Yeah, on all dimension we have. But of course, we have some relation between them, because like every edge, if I'm writing now, like this shape, like I have pyramid here, and I have triangle here, and I have edge here, edge here. So this edge, for example, it's something here, element here. But this element have two vertices, right? What is called like two faces, this face and this face. Or triangle here, like this triangle have three faces, right? This face and this face and this face. Okay, so there is a map that tell you, like D0, it's tell you, like if this is like this edges, so D0, it's give you this, this one, and D1 give you this one. Okay, there is like, you can choose what is the order, D1. Here, every triangle have three faces, so there is a map that tell you how they are glued together. And for more simplices, you have more, right? For pyramid, you have 4 triangles. So D2, D3. And of course, like there is some equations that tell you that, okay, if you get triangle, for example, and you take, for example, this face, and this face is the same as to take this face and then to take this face of this, right? There is some equations that satisfies identify. Yeah, there is, okay, anyway, and but there is for important that also to think about because every point, I can think about this as a edge, yeah, and every edge I can think about this in 2 ways, as a triangle, in this way or in this way, and so on. So you have another map which calls the degeneracy map, but it's not important for this talk, okay? So you can think only about this. Okay, the simplicial, there is another map of degeneracy. It's important for the theory, but for now, for someone know first time simplicial set, so this is what you can think about, okay? So like, for example, we want this to explain this using simplicial set, to explain this scenario, this measurement scenario. So one can choose for every measurement, can choose vertex or point. Okay, I'm using vertex, maybe node I will use here the word, because we are using vertex there as a vertex of a polytope. This is something else. Node, let me say node here. We have this nodes, A1, the measurement, A1, A2, B1, B2. And I can do this, measure this together, right? And this together, right? And this, and this. So I can explain here, this is called the measurement scenario, using topological space. Like how it looks like in this language. It looks like this, like here, x0, it's all the nodes, A1, B1, A2, B2. And x1 is the edges. Okay, let me maybe call the edges, okay, maybe sigma 1, sigma 2, sigma 3, sigma 4. So sigma 1, sigma 2, sigma 3, sigma 4. Okay, there is more actually, the degeneracy one, but okay, I write like this in order just to write something true mathematically, but it's not important for this. This is important, and there is a relation, like we said that there is 2 maps here, D0 and D1, right? So here maybe I should choose direction. So for example, for sigma 1, D0, if I am applying the map D0 on sigma 1, this will give me A1, okay? B1, sorry, D0. But this is the same as to take like D0 of sigma 1, this is B1, which is the same as to take D1 of sigma 2, right? So here, this maps telling me abstractly this picture, yeah? Telling me what happened in this picture abstractly. This is the idea of simplicial set. It's good also because we can talk now about something like this, for example. Cycle like this, because I only choose in x1 only one sigma, And I decided that if I apply, and here 1 point, let's call it's v in x0, and that is the two maps send this sigma. Yeah, the two faces of this is the same. So so it's some flexible language. It's very good language. The simplicial set. It's used in not only for geometry, for homotopy theory and category theory. So people use it in many fields. Yeah. Anyway, so how we can now describe the the probability tables that we have there, the probabilities. So how we can describe this using simplicial sets. So in order to do that, we need what called map between simplicial sets. So this is simplicial sets. So how we can explain map? Okay, someone know a little bit, he can imagine that this is a map between simplicial sets. Like if I have, sorry, if I have this simplicial set and this simplicial set. So a map is like as here, like it sets. So it's again like maps. Some maps in every degree. Map in every degree that makes the diagram commute, like that preserves the face. Like if I'm sending something here, this one sigma to f1 of sigma, I apply d0 on this. So this will give me the same as applying d0 on this and then taking f0 of this. So okay, so there is a relation between. So this is equal to this. So this is the map between simplicial sets. Okay, of course, like this is continuous, like we have more order. So now we are close to define the probability simplicial distribution, like exactly simplicial distribution. Again, this is mean like some generalization of the tables of probability that have non-single link. We are just one thing I want to define. I want to give another example of a simplicial set that it used as an outcome. So the example, it's this, like this simplicial set, x0, it's equal to zm. Zm, like it's mean, like, I mean z. Okay? 0, m minus 1, this field, and this, sorry, ring. So the m cross zm, this will be x1, z. And so on. You understand what I mean? And here the faces map, it's given by omitting. Like I have two faces map here. Like I have AB here. If I am applying D0, so I am omitting the one in the 0 place. So B. If I am applying D1, so it's A. Okay. And here also the same. Like okay, A, B. There is 3 ways to omit one of them. So this is exactly D0, D1, D2. Okay. Something abstractly, maybe someone, okay, you say that simplicial sets that describe some topological space like blue by this. What is this describe? There is some, but we, for now, let's forget about this. But why this is important? This will be instead of the outcome, because if we have m outcome, we want to also replace the outcome by space, because we have measurement space that tell me which measurement I can measure together. I can do the experiment together with this measure. And also here, the outcome I also replace by simplicial sets, by space, topological space, another. So why is this good? Because actually what we are doing, if you remember the table, so what is the tables? Like for this set, the set of x1 here, sigma 1, which is like, what is sigma 1? Again, this is this AB. Maybe it's better to write like this, A1, B1. This will remind you more. A1, B1. Okay, maybe let me write like this, A1, B1, when I mean like this H from A1, or like this maybe. And A2, A1, B2, and A2, B1, and A2, B2. And in fact, I have 4. You remember we have 4 probability table. So probability table, what is this? Like, it's a probability on this set, right? What is this set? This is exactly, this set is Z2 cross Z2, right? So we have a distribution on this, okay? Let's call the set of all distribution by D of Z2 cross Z2. This is the set of all distribution. I mean by this, like D of, if I'm taking some set X, so Dx, I mean like all the probability from X to 0, 1, of course, like probability on X, like the sum of this is 1. Yeah, this is what I mean by D of the set of all the probability on this. So actually we have a map from this to this, right? Because for every H we give probability, right? And here, but this is simplicial set. So we have this D0 and D1 that going to the right to the nodes of this. And here, but actually this we can apply this D, in fact, is a functor, so I can apply on this simply because this is the one simplices of this. So there is also the 0, which is Z2. Because you remember that also we get for every one of this table like this. Do you remember? Like, for example, for A1, there was like what to be 0 or to be 1 was something 3/4, I remember. So we have like this map. And here also we have a map like this. When we apply D on these maps, on D0, D1, we can apply this. Okay, this needs to be done by everyone. Can do this as exercise and see that this is exactly the non-signaling. Like that, this diagram commutes. That means that if I am applying this, like I'm taking this give me a table of distribution on this. If I applying D of D0, applying D0 here, this will be the same, the probability on A1. This is exactly what we did before, right? When we sum what is the distribution is 0. So this is exactly, this will be a good exercise to do, to see that this is exactly to say that this diagram commute. Like there is 2 diagrams here, diagram for D0 and diagram for D1. Okay, there is 2 diagrams. Yeah, because the sum is 1, maybe it's enough one of them to be commute. Anyway, so it's now, of course, like here, because we have one-dimensional, we don't have, in the measured space, we don't have triangles or something, so we don't need the higher dimension. But in general, the definition of simplicial distribution, it's like this. So let me write it here. So the definition of simplicial distribution, simplicial distribution is a simplicial map yeah, this is a simplicial set and this is a simplicial set. Okay, we thought like we can any y, but we will take like this z in order to be more realistic. But again, like we choose first of all, like X is a simplicial set, is simplicial. Okay. And we have this. Of course, in this case, what X called? X called the measurement scenario, yeah, because it's explain me how what I can measure together, right? This is the measurement measurement scenario, and delta Zm is the outcome scenario. Okay. So space. Sorry. Yeah, right. Measurement space. Yeah, the scenario, this is simplicial scenario, like x and y together, x and delta Zm. This together called scenario, like, or simplicial scenario. Anyway, yeah, space, right, sorry. Okay, so we have all this, like if we have, so we will call this simplicial distribution of x delta Zm. This is like all the simplicial maps from x to delta Zm, yeah? Like I mean by this is all the simplicial map. Like I say this is simplicial map, yeah, where this is simplicial map P, yeah. So this is, we call this like this. And we can also describe here, what? Where, in the middle? The one before that. Yeah, here, here D, yeah, right. All the map from X to D of delta Zm, right? Like here, but when we say simplicial distribution, yeah, we mean like this exactly, map from here to here. So this is the notation we use. And now in order to describe contextuality, actually, there is a natural map to describe this. So let me tell you. First of all, this is a convex set, even is a polytope, like if X is finally generated. So this is a polytope, okay? Or convex set at least. Yeah. So, and we have actually, because of this description, we have, this is a distribution here. So we have this map from delta Zm to D of delta Zm, the delta map, delta of delta. Yeah, you understand me what is this? Is mean like every element here in an element, like I send it to the delta map, delta X. Yeah. So we have this map, and this map actually induced like every map from simplicial, every simplicial set map from X to delta Zm. It's going to yeah, you understand me what I mean here? Like here I have a map, simplicial map from X, then I only, so maybe I can call it like this, okay? I only compose with this, then I get simplicial distribution, which is, it's only a simplicial set map. It's not really, there is no distribution because it's delta, like only choose one of them. But we also have, because this is a set by itself, so we can also use the delta in order to include this in this. And now because it's convex, so we have a unique map that extends this. This is like in vector space, like I have here, it's the bases, and here all the convex set of all these, like the span of the bases. So this is the bases determine the map here, the unique maps between vector space, linear map. But here in convex set theory, the same phenomena, the adjoint phenomena. Okay, anyway. So we have this theta, and really this exactly tell me if there is a global, because if you want to think about this, is exactly something here is exactly the global table that we talked about. Okay, one can like, so this is exactly, and this is the map that given from global some simplicial distribution. So some simplicial distribution here, it's called contextual if it's not in the image of theta, of this theta. Okay, so this theta, so like one natural map that tell me if something is contextual or not. Okay. Okay, all of this actually was only to describe the language, but now I, what's the talk about? The geometry of simplicial distribution on suspension scenario. So what we mean by suspension scenario? So in fact, it's on cone scenario and suspension, because we need the cone scenario before the suspension scenario in order to go to suspension scenarios. So the thing is like this, like we talked about this measurement scenario. We talk about bipartite, but we can add more, right? Like we have Alice and Bob, and maybe there is a child, Charlie, who joined to them. This have some. And this also, everyone have measurement, and they do together. Everyone choose measurement, and they do together the phenomena that we described before. And now the goal of this talk to show that actually knowing this about this, it can help us to go to this. How it could be? First of all, maybe this is something that in the older language people didn't think about this because it's not really important. Like when we only added this. Like now I have, I added Charlie. He joined, but he only have one measurement. So even I try to ask like is Salman, you all know Salman about this, because so from from his intuition, because he worked on this, he said it will not added anything, like really it's not important case. And really the first thing that we prove that it's really not added a thing, but it's also important to understand what is mean exactly not really added any new information, what exactly, because it's help us then to understand what's going on when we add more. Yeah, this is the idea. But okay, what it's mean in our language, this is the thing that why this is the language of simplicial distribution. It's helpful here because this one give me space, right? We said the measurement space, like all the things, so this give me some space. Okay, I'm writing like this. I mean, like some, actually it's a graph, like something like graph. But then when I add only C1, like a new one, that this one can measure with any one of them. Yeah. So it gives me what called the cone. You know what cone? Yeah. So topologically is a cone when we add one. When we add two, another one. So this is a suspension. Okay. And we can add more, and this is like something generalization of suspension. Like suspension is two cones together. Yeah. So now we want to use the property of cone and things like this, and what we know about cone, and in order to move from here to here. Okay. And to show, and at the end we will show that in order to study this, what I mean by studying this, to study the polytope that induced from this scenario. Yeah. To study the polytope that induced, we can study this by, if we know about this, the vertices of this and the Bell inequalities of this, and a little bit more things. Yeah. Like everything here can be done here. Yeah, in some way. Yeah, it's not that, but connection between things. Yeah. Okay. So to do this, I want to start with something called joins of, I think, yeah, I finished everything in the beginning. Just a minute. Yeah, I need something, but okay, I didn't talk about, but okay, I will back to this again later. So yeah, let's go to the mathematical things that I need in order to find. First of all, we need something called join. Now I'll describe some tools that I need. So I need a join, the join of convex sets. Join of convex sets, it's the co-product there. Okay, this is the co-product there. So back. So if I have convex sets A1, AM, it's in the convex category. So we define a new convex set. What is this convex set? It's like something here. It's something like this: delta 1 a 1, delta 2 a 2, until delta n a n. When the sum of delta I it's 1, and ai, every ai, it's in a1 ai, sorry, with some point I added to every set's 1 point, one artificial, like I will say why I added this, because it's lambda, and lambda I is 0 if and only if the ai it's equal to this point. Yeah, let me explain what I want. Like it's something like a of this, like it's a convex combination, a formal of the from everyone I'm taking. Yeah, from everyone. Like here, maybe the easiest example to take 1 point and this. Okay, so what is the joins? Only the triangle, because I'm taking like every edge here, it's lambda 1 of something here, which is only this, with okay, maybe I should call it something else, x, something like, I don't know, lambda x, something like this, and something from here, y, let's say lambda 2 y. But if this is 0, if this is 0, like it's okay if I'm taking quarter of this and 3/4 of this, so we understand that it's something here, right? Triangle. So this will give me something here. It's more close to this. Yeah. But what if this is 0? So I don't want x, like to take x here. I will take this, the point that I added. Yeah. When it's 0, that this is not involved. That means, yeah. Yeah, I need this because you can have many points. If you have more here, let me show something. Yeah, let me show. If this is 0, it's important here because you have more points. Like what about this 0? You have many points here, right? Let's say 1, y1, y2, 0, y1, and 1, x. I can choose, and 0, y2, and 1, x. What it give you? Which one it give you in the triangle? Both give you x, right? But I need 1 point for x. So that's what yeah, for this x. I need only 1. Yeah, of course, there is a way like to say that we get, yeah, of course. But I did in this way because I find it in the, what? Yeah, to join of topological spaces, like the joins that we know. Yeah, it's the same. Yeah, it's exactly like the same, but it's like because we want also to describe the convex. It's easy, like by this way, to see the convex structure here of this. Yeah, you can, of course, you can divide as you said. Yeah, like this is the same for us. But in order, instead of say this, they say this, and also I found it in the. It's a good way. I found it in the lecture. I think one paper of Jacob. Yeah. So now what known that actually this, I say this is a co-product, and for people who know category theory, they know that this the D distribution, it's left adjoint. So it's a preserved co-product. So it's preserved co-product. Like if I apply now in sets, like this is a functor from set to set. So we have this fact that D of x1 is exactly the join of this. Yeah. This is something, but it's good also to know what is the map from here to here. What is the map? Like if I have distribution on this, on the union, how I can make it this distribution of everyone. So I will have here P1, lambda, of course, 1 of P1, and until lambda m of Pm. Yeah, I will have this. So what is the lambda? Actually, lambda 1, for example, is the sum of all the probability of P when I go in x1. Yeah, and also for the other. Yeah, so it's here obvious. And this one, it's defined exactly like it's defined like P1 on something here on x and x1. So this is exactly Px, but I should divide by lambda, by this lambda 1. Sorry. Yeah, in order to be the sum is 1. Something like this. Also, like, okay, it's coming from something general that people know from category theory, like because of a John, but also it's easy to prove this using formula. Yeah. Now we want to, the first step that we're doing, we want to generalize this to simplicial distributions. Okay. We want to generalize this to simplicial distribution. Let's do this. So how we can do this? Because you know, like this is a special case. Like distribution on a set is a special case of simplicial distribution. What is the relation? Like simplicial distribution, it's also distribution in many sets that glued together in some way. This is simplicial distribution, in fact, right? So the lemma that help us to prove this is the following lemma. In order to generalize this to simplicial sets, so the following lemma that's saying that if x simplicial sets, of course, x is simplicial sets, is connected. Now, what it's mean connected, because it's there is no really one definition of connected simplicial set. So I mean here, like for every two nodes, you can go by edges. Yeah, this is like in a graph. Yeah, this is what I mean by connected. So if this is connected, then for every just a minute, for what I want to say, like if I have and we have simplicial distribution, it's important. Yeah, it's like this, right? Yeah. We need simplicial distribution, and if and P is a simplicial distribution on yeah, okay, on D. Oh, let me maybe write it in this way, and then we don't need, I don't need to go to bundles. We can write it without this. So let's say it's a simplicial distribution on this, like Y and Y. The outcome here Y, like, and we have like Y, it's summand of this Y, okay? Is summand of this Y. You know what I mean in summand? Like I mean like there is Y, it's equal to Y prime with another Y, okay? Let's say this is the case. Then, okay, this is simplicial distribution. Then if we take like X in Xn and another X in another Xn, like X in X1 here and Xn2, okay, another one, and I taking all the Y on Yn here, one, taking this or taking this will be the same, okay? Nix or X. Then this will be the same because X is connected actually, yeah? So let me explain what does that mean. Like if we have simplicial distribution, so we see like simplicial like simplicial distribution, we say like, okay, there is here, I don't know, X n1 and there may be X n2, yeah? So, and I have this is a distribution on what? On Y of n2 here, and here n1. So here Pn2, there is a map, Pn1, there is a map. And of course, it's related by faces maps. Yeah. So these two are related somehow. These two somehow it's related because it's connected. Yeah. Okay, the proof is a little bit technical, but I try to explain why it's true. And now, if you're taking, like you taking here this one on something, you taking here some x, and you sum all the distribution on this y, all the distribution on all the probabilities on this, yeah, this one, yeah, one prime, yeah, one prime, both. Yeah, sorry, because in one it's one, both will be one, yeah, will be one, yeah. No, in one prime because it could be not one, yeah. In both, in y, as Cihan say, like in y, all y, if I'm taking, of course, it will be like the whole, yeah. Maybe this in one and this in two, I choose anyway, like this is x prime and this is x, yeah. So in if I'm taking this in because it's simplicial, also we use the case that this by itself is simplicial set. We use this. So this will be the same. So this remind you, if you look there, you can look there and look how why I wrote this formula, because this formula to go from here to here, it depends on this, that the sum is one, like I'm summing all things on this summand, yeah, I'm summing all this, but could it be happen when you have simplicial sets, because you have many things, like, yeah, in every degree you have something, but this lemma telling you that if x is connected and you have simplicial over this, so it's okay, like this will give you the same, this is invariant, yeah. So this is depend on, so we can define like delta of p is depend on p and depend on the summand, yeah. It depends on p and depend on the summand. We can define this now. This is one number. It's not depend on which, yeah. Just this.
But then why the summand of itself?
Yeah. Why is summand of cells? Then you take, this is exactly what you said. Like if it's so obvious, like this will be one and this one if you're taking the sum of all of this. But if you take part of this, the sum of this shouldn't be one. It's part of this. This is like here you're taking this. You have distribution on this, but you sum all the probabilities on this only. So it's something, maybe it will be quarter, maybe it will be half, right? But if you take the same thing here, it will be the same. This will give you the same number. Yes.
But I think x is connected, right? Like
Yeah.
It might go inside y prime or y double prime.
Yeah. It's about just help you that x is connected. Actually, it's not.
0 or 1, right?
Which one?
Sums.
No. Something between 0 and 1.
So it can be different.
Yeah, it could be different than 0 and 1. Of course. Yeah, of course. No, you're taking, like, for example, your outcome, it's in delta zm, right? It's z, like this, z2 cross z2 cross z2, let's say this. And you're taking only subset of this. And you're taking only the sum of subset of this, yeah? Or all the things that it's odd, for example. So the sum could be anything, yeah? Anything between 0 and 1. But it's invariant, and this is invariant because of this is connected. Actually, this is proven maybe because there is no time I didn't add this a bundle. This is proven for bundle scenarios even. This is true. Like if you have this for Cihan, I don't know if other know about this. I didn't give introduction on this, but if you have this, like the event space, it's like this, and this is connected, then it's happened. There is invariant, like it's not depend on x that you're taking, yeah. It's depend on this. So this is important now in order to generalize, exactly, to generalize this.
I see. Okay, now I see.
Yeah.
Yeah,
and now we can generalize this and saying that if I have the simplicial distribution on x, and let's say that y, the measurement, the outcome space, it's summand of y1, y2, y. It's a sorry, what is called co-product of this. then it's a join of this is a join of x, y1, yeah, y2, and yeah, it's joined by this. And now why it's true? Because the same formula we can use, because now we have, like, we can go to this, like, and saying we have here lambda. What is lambda? Lambda that depend on this, like p of y1. This is invariant as this lemma showed, and we can then build also p1, p forces, and so on. So this is not something that coming from something theoretically, but it's also we need to work on that they are glued together with this connected thing. So it's give me that this is invariant. So this is what give. So the formula is important here. The formula is important. Now, why this is help in order to noting about the cone, why this is helpful. Now here is the using of here we use the topology that what known in, actually it's in homotopy theory they use this that the cone, if we have a map from the cone of x to y, there is, of course, here x also x should be connected here also in this case. Then there is a natural isomorphism with this and something called the declarage of y, some another factor that act on I will explain this factor, yeah, some another factor. So by this we will move to this, I will show in a minute, but let me show what I mean by the declarage, this one. So if I'm taking, this is y, let's say this is y, the simplicial set, d1, d2, d3. So the declarage of this is to omit this one, and then this will be, it's like we have the cone, but we have another, the path. So the point, the nodes will be the path, yeah. So y1 will be the point. But then we have two maps only from here, y2, only two maps, so I will omit this one, d0. So here, the d0 of the declarage of y, this is exactly the d1 of y. Yeah, and d1 of the declarage will be d2 of y, yeah? So it's something like omitting this, omit this, and omit all these maps, d0, yeah? It's given by this, and so on. So this is the y0 of the declarage. This is the declarage of y0, and this is 1, and so on, yeah? So this is the definition of the declarage, and this is the joint of the cone. So why this is good? Why this is good? One another thing I want to tell you. So the declarage, it's a functor from simplicial set to simplicial sets. But inside simplicial sets, like there is the categories, the category of small categories. So we can go from here to here by the nerve. Yeah, by the nerve. The nerve of category give you simplicial sets. And in fact, we can like take this. There is definition of declarage. I will not write it because there is no meaning to write it, but anyone can do this exercise to find what we have declarage from category to category. Like for every category, it's give you a category. It's not something known, by the way. I searched, it's not really known, but because maybe people didn't use, but because maybe someone will think that the declaration of a category it will be here. It's not a category, no, but it's really a category. And the good thing that this not really commute, but there is okay commute like our natural isomorphism from here. Okay, so we will use also this. So why this is good? Till now, why is this good? You tell us something, but why this is good? So this is good because of the following. If I'm taking declarage, okay, maybe let's do this. What we want to talk about. We want to do this. We want what I promised before, that I want to study this, right? So what is this? This is a simplicial set from Cx to D this Zm, yeah? But this actually, I can move now by this, I can move to X to declarage of this, right? By this. Now, it's not easy to show that this actually commute, because it's not easy. Like applying D on everyone, but declarage what it's doing, it's omitting only things. So it's easy. It's not hard. Sorry, it's easy. It's easy to show that this is commute. So this is equal even. Yeah, simplicial set X D of delta Zm. Yeah. Now, from here, actually, another fact should be known, that this one is exactly, this one, delta Z, is exactly the declarage of, like, it's the basis space of the nerve of Z M, okay? This one, yeah? So this one is simplicial set of X of D of declarage of twice of nerve of Z M, yeah? And now we say that this is isomorphic, like I can replace between them. This is natural isomorphism and between, so I can move nerve to here. So this is isomorphic to simplicial set X D of nerve of the declarage twice of Z M. Yeah. Now the other things, maybe this is the fact that one can see if we have a group. Maybe between this fact I will write, okay, this is one fact that I use, this is one fact that I use. So another fact that I want to use, that if we have a group, if G is finite group, so declarage of G is exactly, sorry, declarage twice, like of C is exactly the sum of declarage, yeah, when X in G, yeah. So we have this, so let's write this. So I can replace this by D of N of, here's the sum, when X in Zm of declarage Zm, yeah. This is a category. So this is a union of category, like a disjoint union of a category. We apply nerve, so it's, we can replace with the nerve here. We can replace with the nerve. There is a place. Group. Yeah, bunch of. Here, this is no. This is this is group. This is a category. No, bunch of categories. No, this will be category, because yeah, this is category, not the declarage of a group. It's not. It's category, not a group. So declarage act of categories, because like every map become object there. So you don't have one object as a declarage of category. I didn't explain this.
Yeah, you didn't, but maybe it's easier to explain for groups what the category is.
You like it's like the declaration of simplicial says, like you taking for groups, for example, or for category, you taking now your object is the morphisms. The morphism is something like this. This is morphism, but this is considered as morphism from F to the composition. It's a little bit technical to that's why I don't want to enter to this. Yeah, it's a little bit technical, but this is also good exercise to find what is the formula of this. That not because it's not obvious, like because maybe someone thinks that if I am applying this, I if there is a large will give me this something here, not category, but there is, you know. Not. What again? Sorry. Yeah. Which one? Here, nerve of ZM, yeah. The declarage of this. No, I replaced between them because yeah. Yeah, you can. Yeah, I didn't thought in this way. Yeah, but there is. But I wanted actually to move nerve here, and then at the end, I will use the nerve. Yeah, but maybe it could be by another way. Maybe I make things complicated. I don't know. So a nerve, it's nerve of this, like nerve of the clash. And we now back to our. Yeah, this we can replace also to find maybe nerve here. I can also replace because it's isomorphic. And now this, the declaration of, we back to delta Zm, yeah? We back to delta Zm, yeah? So this is the thing. So we got that this is simplicial set of x, d of the sum m times of what? Of delta Zm. This is what I want. And this is natural. So we started from this, the cone on this, and we got that is the union of del m times delta of Zm, yeah? The union of delta Zm. This is good because we can now use this, yeah? That when our outcome space is a union of something. This is exactly that, so we can use this. So let me write this.
The collage of a group is just the category whose nerve is E, object. Okay, so the objects are the group elements, and then you have morphisms given by the group elements, which multiplies.
Yeah, given by, okay, yeah. Yeah, we can explain what this is, but so what we have here actually, we have the following, that if we taking simplicial distribution on cone of delta Zm. So this is isomorphic to what? To join, because now I'm using what done there and this. So it's a join of, yeah, you see, it's exactly what I say. Like when I asked Salman, he says this, right? He said it looks like it's when you add one measurement, it's not really adding something. So this is exactly what really adding something. It's this because yeah. Yeah, exactly. But this will be helpful. This will be helpful that we know this, because this actually is it's like we talk about theta, that from here to here, like which is from d of simplicial sets delta Zm, and here we have the morphism for d of every one of this, and join, yeah. Yeah. So we have here theta of join of theta for everyone. So this is very good, because then we can get our first theorem. That's what? Yeah. So there is a map from here to here. Like P, it's going to lambda 1 P1 until lambda M PM. Yeah. So we have theorem that's saying that first of all, P is a vertex if and only if one of these lambda is 1, only one of them 1, and the rest is 0, of course, because the sum of them 1. So there is a j such that lambda j it's 1, and pj is a vertex in where, in this, like in this scenario, in this the x with x, yeah, in here in this scenario, like in simplicial distribution of this, sorry, yeah, this is 1. And 2, it's non-contextual if and only because of this diagram, if and only all of these are non-contextual. P is non-contextual if and only if for every I is so, okay, non-contextual, yeah. So we have this, and this is important now to move to suspension. By the way, this telling something important, that this given us maybe that, okay, there is a no new kind of vertices, because vertex is only something that vertex from there. Okay, there is more vertices, but it's only that product of vertices that we have one vertex from what we have there, like the union of vertices that we have from there. But this is important in order to find the new kind of Bell inequalities. And you can see in the paper it's done, like there is a new kind of Bell inequalities, even because you have a cone like new structure. So you can find, and this Bell inequality appear in every measurement scenario that includes a cone, for example, suspension. Yeah, because every Bell inequality in the cone, it's also in the suspension, right? Like it's also, so this is one thing that by this we can find new Bell inequalities. Yeah. Yeah. From number 2, there is like description of all the Bell inequality of cones. Yeah. But it's will be new Bell inequality because you added the thing. You can find there is technical things, but for CX, yeah, it can known all the Bell inequality of CX using this, but it will be new Bell inequality, not really the same, because like not the same Bell inequality. Maybe I will show you after I will show you exactly what I mean. Okay, it's induced from the non-Bell inequality. If you want to do like to find, okay, what is satisfying, so you will have new, because you have all of them to be non-contextual. You should go to this, like you have P here, which is P, what is the number, like, yeah, numbers of, and you going to here, yeah, which is, there is a formula for this, yeah, and then you ask all of this to be non-contextual. So that means that all of this satisfying the Bell inequality. So this will give you a new kind of Bell inequality because of this involved lambda. Yeah, you will see. I will. Maybe it's easier to show you now. It will take me time to. I mean, I didn't prepare for this. It gets technical a little bit how to move from this to this. It's not that hard. Yeah. Anyway, so this is one of the things, the good thing. But the more important is to go to suspension. So suspension of X, it's this gluing, right? Yeah. Like this is something like ideas that coming from homotopy theory. People do this, like when you have in the cone something, and in the cone something trivial, like map on the cone, it's something trivial, but suddenly on the suspension, you combine them and you get something non-trivial, right? This is something that done. So here, something similar can done, because in fact, we can write this diagram, and this will give you this diagram. Okay, simplicial distribution of suspension of X delta Zn. Because I'm applying simplicial distribution, it will be, things will change. And now simplicial distribution on this, like this square will give you this square, but simplicial distribution of this, we know that it's a joint of things, right? Of X delta Zm join with yeah, right? And now simplicial distribution yeah. And now here, when they're going to this, it's also easy to find what is it will be the sum here. Yeah, the sum of this, like it will be in order to go to this. Yeah, like we have lambda of P1, lambda 1 of P1 here, lambda 2 of P1, but we can, like taking the real, like, or taking, because the sum of this is 1, the sum of lambda, right? So we can take the convex combination inside this, in this. So something here is described as 2 copies of joints, but satisfying something. What it's satisfying, that the sum of this is exactly the sum of this. So we can also describe something here, yeah? So something here, again, like something inside here. What is this, something inside here? It's something like this. P1, lambda 1, P1, until lambda m, Pm, and mu1, Q1, mu m, Qm, yeah, such, but not everything, like it's not only like product of this, no, but that's satisfying that when I'm going to the, when I'm taking the, like the real of this, when I'm going to the simplicial, when I taking this lambda I p I, it's equal to this, to the sum of this convex combination of this, yeah. This is how, so it's described like element here described unique only by in X, right? Like all this distribution on X, such that satisfying this, and this equation where in X, in here, this equation, yeah. So this, but not only, because we have the theta also, it's like corresponding with the map that telling me about contextuality. So we have here also the global. So the global also we can write like this because of this. So we can write here D of simplicial sets suspension of X delta Zm. We have the theta from this to this. So this theta can be described like this, D of join of this and here the same join of this. And here this one. Sorry, simplicial set of X delta Zm anyway. And we have this theta can be described as the join of theta here. And here again the join of theta. And here theta. This. So we can say that something here non-contextual, if and only if this part, every one of this non-contextual, but not only because if something here that non-contextual is something coming from here, but something because this is the limit. This is the limit. So it's they have these two parts that define it. So this coming from something here and this coming from, but maybe these things are not, don't have the same, not give me something here. Maybe yes, maybe. So what decides this if they are coincide on this? Yeah. So we can also define contextuality using this. So we can say that something here is contextual, or this is non-contextual. Sorry, this is non-contextual if and only if every one of these have global. Every one of these have a global, but the global also, if I taking the sum of the global distribution with this, the same lambda and the sum of this global, they coincide. Yeah, this is the thing. So we can describe contextual. Okay, it's not something really applied. Like in application, it's not really like help too much, but it's something good when we compare between some different scenarios and things like this. Theoretically, it's important. This. For vertices, it could be, so one can look at the last section there. There is detecting new vertices in the suspension of some non-scenario, important scenario by this way. So yeah, for vertices is it's more applied. Yeah, we can apply this. Yeah, so that is enough. Yeah, thank you.
Okay, thank you. Any questions? Any questions?
It's long. Actually, sorry about this.
Okay, so are you able to find the vertices of the suspensions?
All the vertices.
Yeah, I mean, say for small cases, say, I mean, does this diagram tell you anything about the CHSH, for example? Because you can decompose it as the suspension of 2 points.
Yeah, for
then you
yeah, it's
then you
easy
can get
for
the
the
PR
vertices. For the vertices, we need not this is gluing lemma, by the way. Yeah, this is like
Yeah.
but there is we have gluing for vertices. You remember, like gluing this theorem of glue, which we so we will talk about this actually in
So
maybe in some talks about gluing.
Are you planning to give a follow-up talk here on this?
No,
or
on
are
this,
you
no.
finished?
But when we're talking about gluing, then I will talk about vertices. Maybe we'll take something like suspension to see
Okay,
what
so
will happen. Yeah, but
vertex support stuff that.
yeah,
So
I
it can be applied here.
Yeah, it can be applied here because it's yeah.
But you haven't tried computing vertices using this method for.
Yeah, I try. Yes. The last section is about
you have
this.
some computations for.
Yeah, there is
for
some
m
computation.
Is equal to, and how many suspensions? Suspensions of what?
What actually it's applied for this case? I think it's for when you take this, like the CHS scenario.
Yeah.
But you do the suspension of this, which will give you.
Oh, I see.
You know this scenario. This is
what's the number of
like Alice, Bob, and Charlie. Everyone have 2 measurements.
Oh, I see. So you know all the vertices?
No, not all the vertices, but there is detecting of vertices. Yeah, but I think maybe this is the only way to find them. Not sure. Yeah, this is important actually. Scenario there is a paper that Salman sent me, like a paper that they computed all the vertices there, but it's really complicated.
But it is numeric result.
Numerically, yeah. No, yeah, of course.
They put it in their computer.
Yeah. But you see that okay, there is a lot of kind of vertices. I'm not sure.
But I think the orbits are not too many, right? I think I think like 55,000 or something vertices, but the orbits are 40.
No, the orbits less. Yeah, something like this. Yeah. But still, they are different, and maybe the Boolean can help in this. Yeah, right.